Hi, thank you for the great introduction and thank you for inviting me. So I'm going to talk about a tool that I built with my collaborators, what we've named Wiggum, that does Simpson's paradox-inspired fairness forensics. And to start, we're going to talk a little bit about what fair machine learning has looked like so far. So first, there was a period where papers on fairness got rejected from the archive, and then they were like, oh no, we should care about this. And now there's tons of papers, and there's conferences doing all of this. And what happened was people started defining fairness. They wrote equations that defined it. Then they could make algorithms that do that, to solve it. And then they started writing impossibility theorems. So pick any two definitions. You can't have them both. We don't know what to do. Social scientists says, well, but the point that you guys do as computer scientists, you want everything modular, you want everything abstracted. That's why you're failing at this. So, okay, we'll just do causal inference. Some of that's great and probably will really help along the way, but there's going to be a time period where we still are deploying things in the world before we have the causal inference. So what I'm working on instead is an approach where we're calling fairness forensics, or we're borrowing the term from Kate Crawford's NeurIPS keynote in 2017. And the idea here is that we really want to have a person look at the algorithms and make those decisions between, okay, well, we know we can't have both types of fairness. Which one's most appropriate in this context? Or we know the world is biased. Do we have enough data that we have a chance at making decisions that aren't going to make the world worse than it already is? But in order to do that, we want to build these tools. We need to have ways of analyzing and interacting with data that don't require programming, because often those of us who are trained to do the programming and the statistics are not as well trained in social sciences and how power dynamics work in the world. But the people that are trained in making those decisions don't want to look at equations or code. So we need to find somewhere in the middle. And so to do that, we've built an interactive visualization tool. And we decided to start with Simpson's paradox, which is a common data fallacy, a place where people make bad inferences, and we think that detecting these type of occurrences could be one type of thing we'd want someone to be able to look for when they're making these judgments for us. And so what Simpson's paradox is this reversal of trends. The classic example is in graduate school admissions, UC Berkeley noticed that men were being admitted at a much higher rate than women overall. They got worried. They handed it over to a statistics professor. Peter Bickle looked at it. He broke it down by department. That's who actually makes the decisions, which makes sense. And he found that actually, in more departments, women are admitted at a much higher rate than men, but women apply to the departments with low admissions rates. So it all balances out. When you marginalize the probability, you add things together, you can have the situation where it could even be the case that in every department, women were admitted at a higher rate, but overall, men were still admitted at a higher rate. So these kind of reversals are things that could worry people. They also can force people or our analytical fairness definitions to make bad conclusions about what it means to be fair. So we wanted to start with building tools that allow a person to do this. And so we built our tool called Wiggum, and it allows you to add, or you load your data in, you can augment it. So sometimes people try to make the really naive approach of, I'll just remove gender, and then my algorithm can't discriminate, except that it can be reproduced. So we want to try to think of ways we can augment that. And then we ask the user to label the data a little bit. So not assign labels per sample, but rather, what do these variables mean? How should they be used to relate? Which ones are grouping? Because the computer can't tell the difference between a binary variable like decision, which you don't really want to group necessarily by, that's your outcome variable, and a binary variable like gender, which you do want to look at grouping by. And then we compute a bunch of trends and provide those back to the user. So we give an interface for users to interact with, explore, and look at patterns in the data, rather than looking at the data itself, sample by sample. And so they can rank it, they can sort it, they can also provide detection. So we can say, okay, they can set thresholds, and we'll say these trends are strong enough that you think you should be worried about them, and they have these problematic patterns in them. And we've integrated all of these pieces into an interactive visualization tool that allows you to poke around in data sets. You can get a detailed view of this actual data after you've sorted and played around and explored the trend patterns, or the patterns and the trends in the data. And so thank you, and see more information about this at poster 4.
And I am a PhD student at MIT, and I study models that estimate causal effect from observational data where the treatment assignment is not at random. Like, for example, a physician is trying to understand what is the causal effect of me putting my patient on chemotherapy. What we usually do in the machine learning community is we try to go for the most accurate estimate possible. And like the cartoon suggests, this is not always very useful. It's often an overkill. So it's not particularly useful for the physician to know, oh, my patient's life is going to increase by 4 years, 6 months, 11 days, and 2 hours, and a couple of seconds. It's usually just sufficient for good decision making for the physician to know, oh, well, my patient's life expectancy will increase by 4 to 5 years. And that's exactly the kind of questions that we're trying to answer here. We're trying to learn models that enable us to make statements like the one that you see on the slide. So if the patient is treated, her life expectancy will be 80 to 85 years. If she is not treated, it will be somewhere between 70 to 75 years. And for this tool to be something that's useful for decision making, we want the false coverage rate to be low, or in a lot of cases, we just want it to be 0. And we say that an outcome is falsely covered if the upper bound that we estimate is lower than the true outcome, or the lower bound is higher than the true outcome. And what we found out is that if all we need are upper and lower bounds of our causal estimates, this is actually an easier task to learn from a statistical learning theory perspective. And the intuition behind our theorem is highlighted in this plot. So the black and gray lines is the true potential outcome, is the true outcome that we're trying to estimate, and it belongs to a complex function class. It's very wiggly, right? But the red and blue lines, these are the bounds, and they give a false coverage rate of 0, so they're really good. But they actually belong to a very simple linear function class. Now, I'm going to very quickly flash our, like a simplified version of our theorem. Don't get scared, just stick with me. So what this is saying is basically that the risk of overestimation depends on this k term. And what you'll notice is that this k term takes as a function gamma. Gamma is related to the confidence with which we want our bounds to correctly cover the data. And the two terms that you want to look at are the two ones that are highlighted. The first one is the complexity, the statistical complexity of the function class that we're looking at, and the second one is the empirical error on the training set. Both depend on gamma, and both decrease as gamma increases. If I've lost you for the last 5 seconds, all I've said is if I want a low false coverage rate with high confidence, then the task is actually easier. Now, the problem that I've described so far is a little bit ill-defined, because if you look at all these 3 plots, they all achieve a false coverage rate of 0. But let me ask you this, which one do you think is better? Raise your hand if you think A is the best one, best fits. Good. How about B? Some people. All right, how about C? Great, good. The fun thing is that you all answered the right question. And this is because the question was a bit of a tricky question. Different bounds or different estimates of bounds will be useful in different situations. So the plot C shows the bounds that are tightest on average. So if the physician wants to make sure that on average I am estimating the tightest possible bounds, then plot C shows the best fits. But if the physician wants to make sure that the worst case scenario is never too bad, meaning the widest intervals are never too wide, then the second plot is actually the best plot. The first plot doesn't look like it's doing anything efficient, though I'm sure you can think of a possible like utility for it. And to account for this difference in possible uses, we flexibly model, or we propose a model that flexibly allows physicians or decision makers to plug in their own utility functions. So in plot B, we were minimizing the maximum interval width. In plot C, we were minimizing the average interval width. Because I've exceeded my math quota, I can't put any more details here, but feel free to ask me about more details at the poster. We tested our model against a bunch of benchmarks, and what this plot shows is the majority of benchmarks actually violate the required false coverage rate, which is denoted by the dashed line. Only our model and one other benchmark are able to achieve the correct false coverage rate, and our model gives a tighter mean interval width compared to the other benchmark. And here we were optimizing for tightest possible mean interval width. In fact, our model does better than that one benchmark that does not violate the false coverage rate at every possible FCR, every possible false coverage rate, which shows that our model is better able to exploit this trade-off that I showed you in the one scary slide. So in summary, we showed that there's a trade-off between the confidence with which we want our bounds to hold and the complexity of the learning task, and our algorithm does better than benchmark, and it's able to exploit that trade-off a little bit better. Thanks for listening, and please stop by the poster later.
Very excited to be here from California. Have not yet taken off coat, but no, actually Ann Arbor is lovely. My parents fell in love here, so that's exciting. Okay, cool. So I'm going to be talking about traffic stops. Why do we care about traffic stops? Because they're the most common way Americans interact with the police. This happens 20 million times a year, so if there's racial bias here, very bad. However, hard to study. 5 reasons why. First, until our work, there was no national data set, okay? So no national database that tracked every time Americans are stopped by the police, so we worked with journalists. They spent about 5 years submitting public records requests to hundreds of different departments. Journalists are extraordinary. Okay, so then you get people sending you data in like every conceivable format you might imagine. If you asked a bunch of police departments for data, that data has numerous errors. For example, in Texas, like Hispanic drivers were frequently mislabeled as white for mysterious reasons. This requires thousands of hours of data cleanup. To save you the effort of doing it yourselves, we've released all the data and all the code so that you can build on our work, and we're very excited to see what people come up with. Great, so now you have the data in a standardized format. Now you can actually start doing math. The first thing you might look at is simply disparities in the data, racial disparities. For example, search rates are about twice as high for minority drivers as for white drivers. You see similar disparities for arrest rates. That by itself, though, doesn't prove discrimination on the part of the police, where discrimination here means treating people differently because of their race, because these groups might differ in many other ways as well. A solution is to look not just at the search rate, but at the rate at which those searches actually find something. Intuitively, that hit rate, if that hit rate is very different between groups, if, for example, it's 90% for white drivers, but only 10% for black drivers, that suggests that the police are searching black drivers on the basis of less evidence. So when you do this analysis, you do indeed find that hit rates are somewhat lower for minority drivers, suggesting discrimination. But problem 4, the hit rate test itself has a problem which is known as inframarginality. Here's a simple hypothetical example to illustrate this. Imagine you have 2 races of drivers, white and black drivers, and within each race you have people who are quite likely to carry contraband and quite unlikely to carry contraband. And these groups are easy to tell apart. Now, importantly, in this hypothetical example, the police are not being discriminatory. They're searching all drivers who are more than 10% likely to carry contraband, applying the same threshold to both groups regardless of race. What's going to happen in this example is that the hit rate for white drivers is going to be 75%. The hit rate for black drivers is only going to be 50%. So it's going to look like there's discrimination on the basis of the hit rate test, even though by hypothesis the thresholds are the same. Why is this happening? Because the statistic we're measuring, the probability of carrying contraband conditional on being above the threshold, is not actually what we care about, the threshold itself. That threshold itself is not observed in the data. We have to infer it using a Bayesian latent variable model, which we call a threshold test. When you do this is my math slide, except I didn't put in any math. Imagine a lot of math here. You quickly run into the problem that you're trying to fit a high-dimensional model with a whole bunch of parameters, and you're trying to fit it using MCMC because you're doing inference. And you're fitting this on this massive data set of tens of millions of stops, and it's extremely slow, like a lot of suffering. I can say this because some of the suffering was my own. So our solution to this problem is to invent a new family of probability distributions, blah, 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 beta, logit normal, tractability, many magical words. Come talk to me more if you want the mathematical details, but the main point here is that the model runs 100 times faster, making it feasible to scale it to a data set of our size. Great. So that's a lot of math, a lot of suffering. Is it actually worth it? I think criminal justice is an exciting application area because it's an area where you don't just write papers, things actually do change. This happened just a couple weeks ago. The Los Angeles Times published a report using our methods where they're arguing that there's statistical evidence of racial discrimination against minorities, and they're applying that threshold test that I just discussed with you. And in less than a week, the Los Angeles Police Department actually announced that they are going to drastically cut back on random stops due to this evidence of racial bias. Great, here are the references. Come talk to me more. Yeah.